Hello Mautas! Welcome to this great adventure, understanding the fundamentals of physics, a long, intense, hard path but also profoundly beautiful and wonderful. And we are starting now with the material of this course. At the second step is the world of dynamics, what it is, how it operates, what it is for. Stay and I'll tell you. Until now, we have looked the other way. When we have described the movement of something, we have played dumb and haven't asked about the reasons. So this is only half of the story. What makes something move and what makes something change the way it moves? All that we have included in the movement, but without delving into the causes, well, the time has come to answer these questions. What makes something move? Roma, I know Mary. Well, the answer is forces. With that, we are completing that story. With forces and their laws, we obtain the description of motion that kinematics uses to study future movement. The study of forces and the laws that describe them is called dynamics. So dynamics and kinematics come together to completely describe motion. And as I say, at the center of this dynamics that feeds kinematics is the concept of force, and with it Newton's three laws, which are its Bible. It's time, friends, to step into the playing field of this great genius. It's time to travel to Woodstock Manor, where Newton pondered these questions at just 24 years old. This genius took advantage of the fact that his university, Cambridge, had closed due to a pandemic to lock himself away for 2 years and reflect on how the cosmos works. He was that odd, unadaptable type who didn't fit in anywhere. One might even say a failure, as he would change history alone, locked in his thoughts. From that seclusion, his laws of dynamics were born, along with his law of gravitation and also his studies on optics. But let's not forget that he was a very strange person. Although he had everything ready at 24 years old, it would take him several decades to publish it, mainly out of fear that others would appropriate his ideas. Thus, he would go down in history with the most important scientific work of all time. It is his Principia of Natural Philosophy, or more commonly known as Principia. Newton had become a true legend, as in those Principia, everything we are going to see in this course appeared for the first time, particularly the concept of force and its use to understand motion thanks to the three laws he compiled, what we now call Newton's laws. This is precisely what we are going to see today. So boys, girls, leave the room, dress well, put on your best and come back, because today is an important day. No, better. It is a very, 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 very important day. It is an epic day. At last, you will understand and know the work of the greatest idol in history, Isaac Newton. No, not just understand. We will deduce them and learn to handle them. And I also have good news, because all this stuff starts from a very simple observation. If you see when two bodies collide or interact, both change their speed in direction and magnitude. Well, surprisingly, it is observed that their change in speed is proportional to their mass ratio. Of course, this is not something I'm making up right now. It's something observed daily in 1,000 things. In billiards, in bowling. It's an experimental fact. We see that when a very massive body collides with a smaller one, the very massive one is barely altered. Its change in velocity is small compared to the smaller body, which does experience a significant change in velocity. This is basically what we just wrote. Nothing more, nothing less. Moreover, the velocity change vector of one is in the opposite direction to the velocity change vector of the other. That is to say, one goes on each side. It is what we see and what we expect to see. Well, ladies and gentlemen, these two sentences are the core of all dynamics, so review it as many times as you need, because there lies the key. From there arise Newton's three laws. So we continue, let's see how. This fact, which is observed and you can see in daily life, makes it very useful to define this magnitude. We called it linear momentum, or quantity of motion, and it is a vector magnitude that is simply the product of a body's mass by its velocity. So what we have observed is that the change in momentum of one body has to be equal to the change in momentum of the other. Wow! Fascinating. We are doing a lot of physics here, but pay attention, this is just the beginning. By playing a little with this simple equation, we can express it in this interesting way. The momentum of the two bodies before must necessarily be equal to the momentum of the two bodies after. This is one of the most important laws of the universe, and is known as the principle of conservation of momentum. This, ladies and gentlemen, is part of the Bible of physics. We are at the altar of our beloved science. Alright, well, based on all this, the first thing we can learn is that in the absence of interaction, a body moves with constant momentum, or, in other words, constant velocity. This, ladies and gentlemen, is Newton's first law. Wow, how simple. It really is very simple. although we will put it in other terms, which is how it is usually found. First law of Newton or law of inertia. In the absence of forces, a body remains in uniform motion or at rest forever and ever. That is, bodies tend to maintain this state of motion. The example usually given is that of a bus that suddenly brakes. Don't you get thrown forward? Yes, due to inertia. You tend to maintain your state of motion. That's why you are thrown forward. Well, the truth is that Galileo observed this law before Newton, and it is one of the great advances in understanding the cosmos. As you can imagine, it's not obvious at all, because if, for example, you kick a ball, after a while it stops. But according to the law of inertia, didn't we say it would always move straight? Well, the answer is that it doesn't move straight because the ball experiences friction with the ground, with the air, which slows it down. The fact is that this issue is not in the absence of forces. What's incredible about Galileo is that he could see an ideal, abstract, and real case and make a law from it. The absence of forces doesn't exist on this planet, but if it did, Galileo says, it would make something never stop. The truth is that Galileo could never prove this. But we, more than 300 years later, can, although here on Earth we have already seen that it is impossible because there is always friction. However, in space then it's different. The probes sent into space continue with eternal motion, just as Galileo predicted in what is known as Newton's first law, this law of inertia. Galileo and Newton were indeed right. So let's move on to the second law. So far, we have related the changes in two particles, particle 1 and particle 2. However, friends, on many occasions we are only interested in the dynamics of one particle governs the interaction with another or others, which we care very little about how they evolve. Their effect, all of them, can be denoted as a force, which is what causes the change in motion. We define it like this. Force is what generates the change in momentum in a particle. See? The interaction of two. The particle we are interested in is condensed under the concept of force, hence the importance of this concept. And this, friends, is Newton's own second law. We call force the change of momentum with time. Since normally the mass does not change with time, we arrive at this usual form of stating this second law, the famous force equals mass times acceleration. Yes, we have it. In fact, we can take the opportunities to confirm something very interesting. In the absence of forces, momentum must be constant. That's right. Again, we have the first law, we are on the right track, and there's not much left. Let's go with the third law. We say that the change in momentum was equal and opposite in sign. If we evaluate this over a certain time variation and make the time interval as small as possible, we arrive at the definition of a derivative. But be careful. Remember that this is precisely the concept of force. With this, we arrive at Newton's third law, the law of action and reaction, or that all forces come in pairs. Whenever there is a force in the universe, another appears in the opposite direction. Always. In fact, this is what we know as recoil, and it creates very funny situations when not taken into account. We use this third law to walk, to swim, to fly. It's everywhere. It's a fundamental of movement that we cannot forget, and with this, that would be all. We have finished the Bible of dynamics. Friend, if you have made it this far, congratulations. By the power that physics grants me, I declare you a child of Newton. Never, ever forget this day, and that's it, you might ask. Is this all? Well, yes, I know, it's incredible that an entire branch of science can fit on a piece of paper, right? That it can be as simple as this and nothing more, yet so powerful? Because these same laws were used to predict the movement of celestial bodies, like Halley, who was able to know when the comet would pass in the year 1759, or Adams and Leverrier, who used it to discover Neptune. But even several centuries later, it remains just as fundamental. It is still used to build buildings, bridges, roads, or rockets, and they work spectacularly without fail. And they will continue doing so for centuries, for millennia, for millions of years. But how do they do it? How are these laws used? Well, don't be impatient, because this is what we will see in the following chapters of this course, dedicated to learning how to use Newton's laws. See you in the next video, Matty. May the action by reaction be with you.